analysis, a simplified version of the packaging machine was created. In this first part, the creation of the assembly will be shown. The machine moves the box on a conveyor belt at a constant speed. Sensors along the path trigger a plate to get released into the box along with a lid for the top of the box. When the complete box reaches the end of the conveyor belt, it goes onto a spring plate that brings it to a lower level. First, download all of the components needed for the assembly from the link at the bottom of this post. Open SolidWorks and create a new assembly by going under File, New, and double-clicking on Assembly. The Begin Assembly Property Manager window will appear on the left side of the screen. Click the Browse button and locate the machine-based part that was downloaded. Click Open and then OK in the Insert Component Property Manager. This will automatically align the part's origin with the assembly's origin. Next, click Insert Components and then add the box part into the assembly. Add a coincident mate between the box's front plane and the front plane in the assembly. Then add a coincident mate between the bottom of the box and the top of the conveyor. Click and drag the box so it is at the start of the packaging machine as illustrated here. Next, click Insert Components and insert the plate. Add two coincident mates between the side faces of the plate and the inside faces of the plate holder. Add a final coincident mate with the top of the plate and the top of the plate holder. These mates are just used to position the part and will be suppressed before performing the motion analysis. Insert the lid part and follow the same mating procedure that was used for the plate. Now insert the releasing plate part into the assembly. Add a coincident mate between the top of the plate and the top face of the releasing plate slot. Add a second coincident mate between the side edge of the releasing plate and the side face of the slot. Make sure to select the edge of the releasing plate. The combination of these two mates makes sure that there are no redundant mates between the releasing plate and the base. Redundant mates are when two mates remove the same degree of freedom from a component. Eliminating redundant mates helps to improve the accuracy of the motion analysis as well as to reduce the chance of errors. The mates used will still allow the plates to move back and forth in the slot. Repeat this exact procedure with the three other releasing plates. Next, add a coincident mate between the two inside end faces of the releasing plates so that they are now touching. Repeat this for the other pair of releasing plates. For the releasing plates underneath the plate, add a distance mate between one end of the releasing plate and the side of the base as shown. Set the separation distance to 3 inches. This will ensure that the plates are initially equally spaced from the center of the plate and will each open in the same amount of time. Repeat this with the other pair of plates, but set the offset distance to 1.75 inches. Finally, insert the balance plate and add a coincident mate between the side of the plate and the side of the cutout where it fits into. Add another coincident mate, but use an adjacent side of the cutout and a corresponding edge on the balance plate. This is similar to what was done with the releasing plates. Finally, add a third coincident mate between the top of the plate and the top of the conveyor belt. Expand the mates folder. While holding the control key down, select the mates used to mate the plate and the lid. Select the coincident mates between the two pairs of releasing plates and the distance mates as well. Also select the two concentric mates between the box and the conveyor. Finally select the coincident mate between the balance plate and the top of the conveyor. Right-click on one of these and select Add to Folder. Rename it to say Initial Positions. This folder can now be suppressed by right-clicking on it and clicking Suppress. It can be in the Study 1 tab at the bottom of the screen. Under the drop-down at the upper left of the pane, select Motion Analysis. We will first create solid body contacts between the different components in the assembly. These are used to simulate contact as well as friction between the parts. Click the contact icon located at the top of the bottom pane as illustrated. In the window that appears, select Use Contact Group. In the first box, select all the parts except for the balance plate and the base as shown. Click in the second box and then select the base of the packaging machine. Under the drop-downs for the material, select Steel Dry for both. Click OK in the Contact Property Manager window. Create another contact between the lid and the two releasing plates below it. Use dry steel for the material as well. Add a third contact between the lid and the two releasing plates as shown. Use dry steel for the material. Add another contact between the box, the plate, and the lid using dry steel for the material as well. Create the final contact between the box and the balance plate, again using the dry steel material. Next, add gravity to the simulation by clicking the green apple icon. Make sure that gravity is in the negative y direction. When that is set, click OK. We will now add a linear motor, also known as a linear actuator, to simulate the force of the conveyor belt on the box. Click the motor icon. Select Linear Motor for the motor type. Select the face of the box nearest the end of the base as shown. Choose Constant Speed under the Motion heading, and then set the speed to 4 inches per second. Click the reverse direction icon so that the arrow is pointed as illustrated. With that set, click OK. Add another linear motor and select the end face of the first releasing plate. Make sure that the arrow points away from the plate. Under the Motion heading, select Servo Motor from the drop-down, and then select Displacement. Click OK and follow the same procedure to add servo motors to the other 3 releasing plates. We will now simulate a spring on the bottom of the balance plate. Click the spring icon. In the window that appears, select the bottom of the balance plate and the bottom of the hole that the plate goes into. Calculate out the spring constant by using the formula K equals negative F over X, where F is the force being applied to the balance plate and X is the distance that the spring displaces. In our case, the force would be the weight of the balance plate along with the weight of the box, the lid, and the plate. X is the maximum distance that the balance plate needs to travel in order for the box to continue down the ramp. Once the spring constant is determined, it can be used along with the weight of the balance plate to calculate the displacement due to only the balance plate. This distance can be then added to the default free length of the spring in order to determine the actual free length, so that the plate will sit even with the top of the conveyor. When you have determined these values, click OK to add the spring. The calculations and values needed for the spring will be shown in the next part of this series in order for you to compare your own calculations. Select the Motion Study Properties icon in the Motion pane, and under the heading for the motion analysis, deselect the box next to Animate during calculation. Click OK to close the Property Manager. This will help to reduce the time it takes to calculate the study. Next, we are going to add sensors to the model. These sensors are used to detect when a specified object, like the box, crosses its path or when it is a certain distance away. In the event-based motion study that will be created, these will be used to trigger certain procedures to occur. To add a sensor, right-click the sensor created in the last part in order to open it. The spring constant that had to be calculated in the last part is 1.8889 pound force per inch. This was found by adding the weights of the box, plate, lid, and balance plate and dividing it by the travel distance of the balance plate, which is about 9 inches. The mass of those parts can easily be determined by using the Mass Properties tool in the Evaluate tab of the Command Manager. The free length of the spring is 18.4387 inches. This was calculated by using the spring constant and the weight of the balance plate to determine the amount that the spring compresses due to the weight of the plate. This was then added to the default length of 16.8875 inches, which was provided when the spring was created. The new free length of the spring makes sure that the balance plate will sit even with the top of the conveyor. Drag the top key of the motion study so it is on 32 seconds. This will be the length of the motion simulation. In the far upper right corner of the motion study pane, select the event-based motion icon. Click here to add in order to add the first step. In this step, we will set all of the motors except for the one on the box to have a displacement of 0 inches. This is so that they will not initially start moving. Leave the trigger as time and set the time/delay equal to 0 seconds. Click the symbol with 3 dots under the Features heading, and under the Motors heading select all the motors except for the one in the box. Click OK. Under the Action heading, select Change from the drop-down. Set the value and the duration both to 0. Add a new step. For the trigger, select the first proximity sensor. This is the sensor that is below the plate. A delay will need to be added in order to make sure that the box is centered underneath the plate. The delays will be calculated out at the end. Under the Features tab, select the 2 motors that are associated with the 2 releasing plates under the plate part. Set the action to change and set the value to 5.5 inches. Also, set the duration to 0.55 seconds. Add another step and set the trigger to be Task 2, which corresponds to the sensor task. Set the condition to task end so that this step will start after the previous one finishes. Add a delay of 0.2 seconds to allow the plate enough time to fall past the releasing plates. For the features, select the 2 motors associated with the releasing plates that were chosen in the last step. Set the action to change. Set the values to negative 5.5 inches and the duration to 0.55 seconds. This will close the releasing plates. Add another task that is triggered with the sensor below the lid. Select the 2 motors associated with the releasing plates under the lid. Set the value to 6.5 inches and the duration to 0.65 seconds. Add a task to close the releasing plate. Make sure that the value is set to negative 6.5 inches and there is a delay of 0.2 seconds. Add a final task that has a time trigger of 28 seconds. Under the distance can be determined by using the measure tool and measuring the distance from the top of the releasing plate to the top of the box. The box is falling only under the force of gravity, so the equation of motion shown can be used in order to determine the time it takes the box to fall. The box has no initial velocity, as it is resting on the releasing plates. The value of t can be solved for, which results in a time of 0.232 seconds for the plate to fall. Final delay can be calculated by subtracting the time it takes for the plate to fall and the duration of the step from the time it takes the box to travel the 6 inches. This results in a delay of 0.72 seconds. For the 4th task's delay, the same process can be used. The travel time of the box will be the same as found before, along with the time it takes the lid to reach the top of the box. This is because it falls the same distance in order to reach the top of the box. The value that changes is the duration of the step, which is 0.65 seconds. Subtracting this and the lid fall time from the travel time of the box results in a delay of 0.62 seconds. With the study calculated, the study can be run to double-check the results. The playback speed can also be increased by going under the drop-down menu shown and selecting a new speed. Data from the simulation can be plotted by selecting the Results and Plots icon. For example, the vertical velocity of the plate can be plotted. Select Displacement Velocity Acceleration from the first drop-down. In the next drop-down, select Linear Velocity. From the third drop-down, select Y component. Finally, select the top face of the lid and click OK. In the plot, you can see 3 spikes in the velocity. The first one is initially when the study is run. This is when the plate drops from the original mated position to the top of the releasing plate. The next spike is when the plate falls into the box. During this time, it reaches a maximum speed of about 111 inches per second downward. As it hits the bottom of the box, it bounces up with a positive y velocity before settling. The final spike is due to the box assembly moving on the spring plate. This data can also be exported by right-clicking the chart and selecting Export CSV. The data can then be opened in a program such as Excel.